2.44D tensor analysis for points and vector fields on a manifold. So far, transformation has been considered at a point. Now consider tensor at other points, everywhere in fact. There is now the possibility of moving about and of transplanting vectors. Vector fields in affine and Riemann space. A tensor field is the assignment of a tensor to each point of the space. 2.4.1 Vector transplantation and affine connections. Consider epsilon bar to the I equals the partial derivative of x bar to the I with respect to x to the k power epsilon to the k power.
Where vector epsilon bar to the I is not a constant over the space, since partial derivative of x bar to the I with respect to x to the k power is arbitrary. Covariance requirements on a vector field epsilon to the k power taken to be constant is then possible. Starting with a vector epsilon to the I of constant components in an original coordinate system x to the I, we see that epsilon bar to the I in another coordinate system, generally, does not have constant components over the space. Let us now see how the components epsilon bar to the I vary when we go from one point to a neighboring one in space along a curve parameterized with a parameter p. To do this, we differentiate epsilon bar to the I equals partial derivative of x bar to the I with respect to x to the k power times epsilon to the k power with respect to p. Remembering that the epsilon to the k power s are constant along the curve by assumption. See equation 2-23.
Where gamma bar sub mj to the I equals the partial derivative of squared x bar to the I with respect to x to the k power partial differential x to the script L times dx to the script L over partial differential x bar to the m times the partial derivative of x to the k power with respect to x bar to the j. Thus, see equation 2-24. And this defines a general law for transplantation of the vector epsilon to the j at the point x into the quantities epsilon to the I plus d epsilon to the I at the point x plus dx. It is a law of affine character. That is, it has invariant structure under a linear transformation of the coordinates.
So far we have achieved vector transplantation. D epsilon to the I equals gamma sub mj to the I dx to the m epsilon to the j. Now to make it coordinate invariant. This will force certain requirements on the gamma sub mj to the I. To start, we have see equation 2-25. Since we require epsilon to the I times x plus dx to be a vector, this requires see equation 2-26.
So, see equation 2-27. Expanding using a Taylor series. See the next equation. Thus, see the next equation. See equation 2-28.
And since see the next equation, we have see equation 2-29. And using see the next equation, this becomes see the next equation. Thus,
see equation 2-30. These coefficients are called coefficients of affine connection. Note that the transformation law is inhomogeneous in the coefficient gamma sub alpha beta to the I. So not a tensor. This is fundamentally different from a tensor transformation law, and the connections are not tensors. Let's consider the consequence of this non-tensorial behavior. 2.4.2 Parallel displacement, Christoffel symbols. Now we focus our study on Riemann spaces. Consider the metric requirement that the scalar product of two vectors be invariant under transplantation. See equation 2-31.
Using derivative of epsilon to the I with respect to s equals gamma subscript L r to the I, the derivative of x to the script L with respect to s times epsilon to the r, and the derivative of 8a to the k power with respect to s equals gamma subscript L r to the k power, the derivative of x to the script L with respect to s times 8a to the r. This becomes see the next equation, or see the next equation, with relabeling dummy indices to get see equation 2-32.
By permitting the indices ik script L2, additional equations are found, and solving for gamma sub ki to the r, we get see equation 2-33. Define. See the next equation. This is a Christoffel symbol of the first kind. Also define. See the next equation, which is called the Christoffel symbol of the second kind. Thus,
see the next equation. And the law of parallel displacement in a metric space is thus. See equation 2-34. To put this into context, Consider the evolution in time of a mechanical system described by generalized coordinates the I of x of t, x to the I equals d the I of x of slash dt, t equals 1/2 g sub I k of x to the I of x to the k power, and v of x to the I, which gives f sub I equals negative partial differential v divided by partial differential x to the I. As usual in analytical dynamics, we take t dt squared equals ds squared to define a metric on the space of the generalized coordinates, which is called configuration space. Using L equals t minus v, and d over dt times, the partial derivative of L with respect to x to the I, equals the fraction with numerator partial differential and denominator partial differential x to the I we then get.
See equation 2-35, or see equation 2-36. And using the Christoffel notation, see equation 2-37.
2.4.3 Geodesics in affine and Riemann space. Suppose we have. See the next equation. And we parameterize by q. See the next equation. dx to the I divided by dq is a particular tangent vector, while a more general one is lambda of q times the derivative of x to the I with respect to q, where lambda of q is an arbitrary function of q. In which case, see the next equation.
If we let dp equals dq divided by lambda of q, then see the next equation, and we get see the next equation, which define geodesic lines in an affine space. The defining equations for a geodesic in Riemann space become see equation 2-38.
2.4.4 Geodesics as stationary curve between 2 points. A geodesic can also be defined as the stationary curve between points, if the action is. See the next equation. Then, see equation 2-39. Choose p equals s arc length to get. See the next equation. Or, see equation 2-40.